Design intent is the intelligence we as designers build into our CAD models so that they'll change predictably. The issue is, in a history-based CAD system, nobody knows what the intent is other than the original designer. This can prove to be problematic if the designer is no longer available or doesn't remember how the part was put together. Let's take a look at an example. Here we have a view and markup of an old part that needs to be modified. First, we'll make these changes as you would in most any other CAD system, using a history-based approach. Then, we'll go back and make the same changes using synchronous technology for comparison. For our first change, we need to add some extra material to the slide in order to create additional clearance between features. We have instruction to change our slide body to an overall height of 31 millimeters. As you can see, this feature sketch is fully defined and we can quickly make this change by simply clicking on the 29mm dimension and then adding 2 millimeters to it. Solid Edge's dimensioning tools allow us to input formulas directly. Not necessary here, but we've all pulled out the calculator before. Due to inappropriate design intent, notice that our cut has been shifted. We'll need to go in and fix this. This can easily be accomplished by deleting out the incorrect sketch relationships and then adding new ones. Now let's go to our markups to see what the next revision is. Here we're having some problems with deformation within the cylinder and the bottom cutout due to material thickness. Therefore, we need to maintain 4 millimeters of stock between the cylinder slides and the cutout. Our first order of business is finding out how much material we currently have between the cylinder and the cutout. A quick measure gives us a value of 2.5 millimeters. We need to make this a total of 4, so we need to add 1.5 millimeters to the radius of the cut. Another simple change of our dimension value allows us to see that we need a radius of 14 millimeters. It's clear that the original design intent wasn't set up for this type of change, and we now have interference with our slide positioning holes. Undoing the change allows us to go back and alter the way the profile is drawn to correct the design intent. Unlocking this 1.7 millimeter dimension means that we can add a smart dimension between the bottom of the cut profile and the center point of the arc, ensuring that the material is added to the bottom of the cut rather than pushing the arc and the cylinder higher up into the part. Once our correct values are in place, we can see that we're getting our desired results. Now let's take a look at our final revision. We need to fix an issue we've been seeing from our new manufacturer while drilling these counterbore holes. We need to add a bit more clearance between the counterbores in order to not have any blow-through while drilling. For proper positioning in relation to the slide cylinders, we need to move both holes 1 millimeter in opposite directions of one another. In order to get a better idea of what we're working with, we're going to create a section view through the holes needing editing. This is a great tool for parts with complex internal geometry. Using the dynamic clipping plane option allows a section to be shown in any particular location on the part, as well as the geometry located within. Now that we can see where the blow-through is occurring, let's edit this front hole. Once again, by editing our profile, we can either key in exact values for dimensions or let Solid Edge do the calculation for us. Now that we've subtracted 1 millimeter to the front hole, we need to do the same with the top. Repeating the same steps, we notice that this hole is not defined the same way as the previous. This counterbore is modeled as a cut and is concentric to the smaller hole running through the slide cylinders. This sort of frustrating situation is often run into in history-based modeling. Design intent may not be what you naturally expect. It's all down to the original decision upon creation. Re-examining our part to make sure everything is how we need it, we notice that we now have an issue relating to the back cylinder. Again, the setup of the original design intent means that the model hasn't changed as expected. We anticipated the back hole to stay in line with the front hole edited earlier. As we look at the profile, we can see that the hole has simply been dimensioned to the bottom of the part to match the dimension on the front side. This independent type of design intent is tedious and time-consuming, especially on complex parts, and in certain situations, a simpler solution would be just to remodel the part from scratch. However, in this situation, a quick horizontal relationship fixes our issue. In summary, we've made the required revisions, but not without time-consuming interrogation and modification of the original design intent. What if Solid Edge could recognize the model's design intent automatically to give more sensible results during edits? Let's make those revisions again using synchronous technology. We can of course create our designs from the ground up using synchronous technology. However, if like in this case, the design work has already been completed history-based, we can simply convert to synchronous. We just select the last feature, which will move it and everything above it in the history tree over to synchronous. The first thing you'll notice about working synchronously is that we don't have to edit profiles of any features. Instead, we can simply dimension directly to faces, and we have full control over which way the edit is intended. While we're making edits, you'll see the icons at the bottom of the screen light up. This is the design intent recognition. Solid Edge captures design intent based on the geometry, without any additional work on our part. In this change, Solid Edge recognized that this part was created with the top and bottom faces in line with one another. If for some reason we wish to change the recognized design intent on the model, it's as easy as clicking on the relevant icon to relax those geometric relations. First revision done, and the design intent of maintaining a central position recognized. Our next edit is dealing with the clearance between the bottom cut and the slide cylinder. Using our dimension tool again, we can quickly pick up the two radii and choose which face we want to make the edits to. Locking them ensures that they're maintained after the fact. This time, notice that symmetrical design intent was looked after without any outside action on our part. Our final edit required us to use a section view in the history-based model. This was our means to see exactly what geometry and features we were working with. Now, what if we could take that a step further, automatically creating sketches at a particular section and allowing us to use those sketches to drive the model itself? I introduce you to synchronous live sections. Knowing that we need to add clearance between the counterbore holes, but also maintain the design intent further on down the part, we're not going to add just one, but a couple of live sections to the center lines to properly display and represent these features. Quickly turning off our design body, we now have an unobscured view for our required edits. We can simply drag this profile to see how the design intent is being taken care of, which of course is also modifying all of the solid geometry in the background, or we can use precision tools to make the edits. Again, we'll use the dimension tool to enter the precise value, choosing a symmetric input. Remember the multiple moves and multiple profile changes in the history-based approach? That's not the case here. To recap, what we saw here was synchronous technology in Solid Edge recognizing and maintaining design intent on the fly, giving us sensible and predictable changes, overall allowing for faster revisions.